This is the second part of my overview discussion on the pharmacokinetic parameters. Here, particularly, I will discuss about the elimination rate constant, or the KE, and the clearance, or CL. So in both cases, the KE and the CL are parameters related to the estimation or study of elimination. Okay, well, that's kind of obvious. And if we remember our pharmacokinetic graph, if we have the x and the y axis, right? Wherein at the x axis we have the time, and the y axis we have the concentration. We remember that most of the time our graph would look like this, because this would represent the absorption phase, and then this would represent the elimination phase. And this goes down because this represents the amount of drug that is finally being removed from our plasma concentration, right? However, it will be interesting because in some cases, our pharmacokinetic plots would have our will have our time versus concentration graphs in this kind of shape. Okay, it's curved, whereas sometimes we have time versus concentration having a straight descending line. Okay, and that would be significant because if we have, for example, let's say we have like 1 hour, 2 hour, so this would be in hours, 1 hour, 2 hours, 3 hours, 4 hours, 5 hours, and then let's say this is the 100% of the concentration in the plasma, and then this is like half, right? So 50. We're just making estimates right now, and this is 25%, and we could just do the same here and here and here. Okay, before we even go to the discussion of the elimination rate constant and the clearance, I want to distinguish between these two. Now, how will I do that? Since I mark here 150 and 25, let's try to determine the times at which we achieve these levels. So of course, for both the graph at the left and the right, at time 0, okay, the starting point, we have 100% of our drug concentration. Now, how much time in the left graph did it take for us to get to 50? Well, if we trace this here, it would take only 1 hour to reach 50%. But here, how much would it take from hour 1 to get to 25%? So if we trace that here, it actually requires only 2 hours from time 0 to reach 25%. So in 2 hours, we have 25%. Okay. And even if we go something like half of 25, like 12.5%, if we trace it down here, of course, this is not like a perfect diagram, but we will see that at the 3rd hour, we have only 12.5%. And since we can see here that every hour we have the value dropping down to half, right? From 100, it went to 50, and then it went to 25, which is half of that. And then it went to 12.5, which is even half of that. It's like saying that we can see here in this kind of diagram a time wherein the amount of drug will be reduced by half. That's why in pharmacokinetics, another very important variable, which is sometimes the result of deriving the elimination rate constant, okay, or a prerequisite that is to getting the elimination rate constant, is the quote unquote half-life. Okay, which basically is the life or the time required for the initial concentration to go down by half. And here, since we see that every new hour the drug concentration goes down, I could say that the half-life, or the T1 half for our graph right here, is only 1 hour. And remember this, guys, the only times that we would have, there are times that we would have a specific half-life, but sometimes, in some cases, we don't have a real half-life, so to speak. How about for this graph? So from 100 to 50%, how much hours did it take us? So 1, 2, 3. So it took us 3 hours to go from 100 to 50%. Then how much did it require us to go to 25? Ooh, from 3, it only took us 1 extra hour. So that's at hour number 4 to go to 25%. So if you count that from 0 to 3, it required you initially 3 hours to go to half. and then it required you 1 hour. So that's 3 hours at first, and then it became 1 hour later on. And if you even go down further to like something like 12.5, okay, you would see that, I mean, again, this graph is not perfect, but most likely it would even be lower than 1 hour. So probably uh, like 4.5 hour, it would be 12.5. And what's the point I'm trying to make here? Right now, as it is, the initial half-life was like 3 hours, right? 0 to 3 hours, you get 50%. And then on the second halving, like the second time you cut it down by half, which is 25%, it only required you 1 hour. And now the question is, which of these is the true half-life? Is it 3 hours, 1 hour, or like 0.5 hour? And now the answer to that is, if you cannot have a constant time wherein the value goes down by half, then there is no half-life to speak of here. Such case is not applicable. So it is now important for us to realize that the shape is not the only thing that differs in these two, but also the existence of a real half-life. Because in this curved plot, there is a half-life, but here there is none. And in that case, we also have terms for that. Such kinetics or such movement or progression in elimination where there is a constant half-life, so meaning there is a real half-life, is the so-called first order kinetics. Okay? Wherein there is a constant portion, and by portion, I'm talking about percentage, half. Half is 50%, right? There's a constant portion, or sometimes you can even call it fraction, being removed for every unit time. Okay? Whereas if there is no real half-life, that is something that you call a zero order phenomenon, or it's zero order kinetics, wherein instead there is a constant amount being removed per unit time. So for example, okay, a while ago we might have been quite obsessed with just trying to know if there is really half-life, or we were tunnel visioned with just computing things going down by half. But why not try to, again, this is not a perfect graph, but why not try to identify how much percent is being lost every hour? Look at this. From 100, after the first hour, how much did we lose? Probably here from 100, it became 80%, right? And then at the second hour, how much was lost? It's a little, it's not in the middle. I mean, this is not a perfect graph, but let's just take this as something like 60%, right? And then after the third hour, okay, let's say it's something like 40%. Now, based on the pattern of what I'm writing here, what point am I trying to make? The fact that every hour, there is a constant percent being removed, but not 50. In this case, it's 20%. From 100 to 80 to 60 to 40, that's the constant amount. Okay? So here, the keyword for first order is the portion or the fraction, wherein every half-life, the fraction we're talking about is the half, half, half. Here, the constant part is the amount. And this is where many people are really getting confused. Like, fraction versus amount? So in that case, it's like saying here there's a somewhat exponential decrease, right? Because when we talk about percentages, when we talk about this, right, this kind of graph, it happens in exponents. Wherein here it's more of like arithmetic, because like it's like the ticking of the clock. Every single second will equate to the same exact amount of time, and that's what happens. 1 hour you lose 20%. Second hour you lose 20, third hour you lose 20, 4 hours you lose 20. But here, look at this. First hour you lose 50%, second hour you lose 25. So technically speaking, losing 50 and losing 25 are not the same amount arithmetically, but exponentially, or in terms of percentage computations, they're more similar. And I'm not even sure if that's the best I could come up with right now, but because of the importance of this topic, I thought that maybe it would be nice to stop here and to reserve the actual discussion of the KE and the CL at a separate video.